Process design. Many chemical engineers feel that process design is the most interesting kind of work in their profession. Currently, the training chemical engineers receive in college is more concerned with design than with any other aspect of chemical engineers. Most of the information needed by the process design engineer is generated during the R&D phase, particularly from pilot plant data, but that information is based on small-size equipment, whereas the production plant will contain full-size equipment. Adapting that data is known as scale-up. This is always a mathematical technique, but the exact produce used depend on the type of equipment being scaled up. Producers of doing the job are available textbook and handbook, and many frequently be found in manufacturers' catalogs and other such literature. Almost any chemical process plant includes a vast array of pipes and vessels, with other odd-shaped pieces of equipment here and there. Open vessels are usually called tanks too. When heated, they are sometimes called kettles. Plants that process large quantities of liquid raw materials such as petroleum refining plants often have a number of enormous tanks arranged in an are known as a tank farm, where the contents of these tanks are flammable. There are usually embankments of earth-hold dikes around them of the tank's lid, and the material catches fire. The flaming liquid cannot spread over the entire plant, as it did in early disaster. Piping is an important part of any chemical process plant because there is so much of it. Most home piping is of small size and is put together by screw threads cut into the pipe. Screwing section of pipe together is easy to do with small size pipe because it can be easily handled, but the pipe used in process plant generally range in size from 2 to 12 inches in the diameter, and a section of such pipe may weigh many hundreds of pounds or kilograms. Large diameter pipe is put together by means of welding or pipe flanges. When flanges are used, they are usually welded to the ends of the pipe. The flanges have a ring of hole around them, so the two flanges can be bolted together with a gasket in between. Flanges have two advantages. First, welding can be done on the ground or in a shop. Second, the pipe can be easily disassembled for inspection or replacement. The disadvantages are that the joints sometimes leak and the flanges are expensive. Welded pipe is harder to assemble because the weld must often be made while the pipe is high in the air or in awkward position. A good welded joint will not leak, and welding is a cheaper way of assembling pipe than flanges. However, the pipe must be cut and re-welded if it has to be opened for inspection, or if it is necessary to replace faulty section. Pipe is made with walls of various thicknesses. Thicker walls are required to carry materials under higher pressure. Part of the design engineer's job is to calculate the pressure a pipe will have to withstand and to specify walls of the proper thickness. There are a number of pipe fittings used with a piping system. When a pipe must change 90 degrees in direction, a pipe elbow or 90 degrees L is employed. 45-degree L change and the direction by 50 degrees. When one pipe joins another at right angles, the junctures is made with a pipe T. A pipe cross joins four species of pipe. Pipe of two different sizes can be connected by reducers or pipe reducing fitting. When pipes must be joined at a sharp angle, a pipe lateral fitting is used. As with pipes, vessels that withstand high pressure must have extra heavy walls. These are known as pressure vessels and must be carefully designed and constructed. Failure in pressure vessels may result in explosions with large pieces of the vessel flying around the plants, a circumstance exceedingly dangerous to personnel and destructive to equipment. Therefore, the design and construction is pressure vessels, usually defined as those contain above 15 lb or pounds, 0.01 kilogram force, or 9 or 100 kilopascals. Is usually regulated by laws known as pressure vessels codes. Any governmental body will write in own code. In the United States, most are adopt the Pressure Vessels Code of the American Society of Mechanical Engineers, or ASME, which is then enforced by governmental pressure vessel inspectors. This code defines the way in which a design engineer must calculate vessel wall thickness, and shapes, and also set up fabrication procedures to be followed during construction. I'm sorry. Welding, for example, must be done with extreme care and skill. Generally, welders who work on pressure vessels must pass a special test and are then known as certified welders. After a vessel has been designed and built, it must pass a pressure test conducted under conditions spelled out in the pressure vessels code. Because of the complications surrounding pressure vessels, the process design engineer usually design only large or specialized vessels. Smaller ones can be purchased in standard size from manufacturers who specialize in such equipment. These vessels carry a special nameplate certifying that they were built according to the code and that they have passed the required tests. Designing process plant equipment requires more than scale up or following design codes. It also means specifying the materials to be used for equipment. Actually, the material must be selected before the equipment is designed because design is related to the strength of the various materials of construction. Most chemical process equipment is built from ordinary steel, cold mild steel, or carbon steel, but many chemical attack mild steel, causing corrosion. When this is a problem, the design engineer usually turns to stainless steel, an alloy of iron, nickel, and chromium. Some stainless steel contain other metals such as molybdenum that give the alloy great strength, resistance to corrosion, or another desirable property. When corrosion problems are too severe for stainless steel, the engineer may choose alloy that contain large quantities of nickel, known as high nickel alloys. The special alloys are usually sold under trade names. Some are Hastelloy, Incolloy, and Inconel, and may cost as much as several dollars a pound. Some processing conditions require more specialist metal like titanium, tantalum, or zirconium. These are called exotic metals and are also very expensive. In addition to metal, the design engineer has a large number of non-metals to choose from. These include glass, plastic, graphite, and ceramics. Alone or in combination like glass-lined steel or rubber-lined plastic, the graphite used in process plant is usually impregnated with plastic and is known as impervious graphite. There are limitations to the use of non-metals. Most are not as strong as metal, so they cannot be used for high-pressure equipment. Nor can they withstand high temperatures. A process plant is usually designed in several stages. After the research and development has been done, And before the decision is made to build a full-size plan, a final economical evaluation must be made. Of course, economic evaluation were made before and during the R&D work, but they could be little more than educated guesses. The first time there is enough information to make a firm estimate of the cost of the plants and the cost of producing the product in when R&D is complete. The cost of the final product is based on two things: capital investment and operation cost. The first is the cost of the land, the plant, and its auxiliaries such as roads, railroads, ports, electrical power lines, and sewage treatment facilities. Include here is the cost of equipment, material supervision, labor, and design. The total of the cost, a large sum of money that must be available at one time, is the capital investment. The second, operation costs include the expense of running the plants after it is built, raw materials, labor, and supervision, maintenance, shipping, and so on. To determine whether or not an operation will be profitable, the design engineer must calculate the rate of the return or return on investment atau ROI as follows: percent ROI net annual income minus net annual depreciation per capital investment plus R&D cost D with 100%. Annual depreciation is the annual loss in value of the plant and its equipment owing to wear and obsolescence in the chemical process industry. It is commonly required that a project have an estimated ROI of at least 20% after income tax before it will be approved to construction. Thank you.